We can plug in for FA. We have this formula, e to the minus 4r dr. Again, if I wrote it as minus 4x, does it make a difference?
No.
No, because x and r are the same thing. So that's fine. If you wanted to write this equation as f dot dx, same thing. I'm just, again, going with what appears on the AP sheet. Although I'm still annoyed because they have not released the 2013 formula sheet yet. So.
Do they update it every year?
Every couple of years, but the last one on there says 2012, and it doesn't say like 2012 and 13, so I keep waiting to see if there's going to be any changes, but the last time I looked, which was only this week, they hadn't updated it yet, so I don't know what they're waiting for. But anyway, limits on this form, on this integral will be 0.25 to 1.25 meters. We're going to integrate this e to the minus 4r. Technically, this is u substitution, though if you're all pretty good at u substitution already, you probably do it in your head. Yes? No? Maybe?
No.
No? So we'll do it. We'll say u is going to be minus 4r. Then du dr will be minus 4. So therefore, dr is du over minus 4. So we can do the substitutions. So we'll get 0.25 meters to 1.25 meters. E to the u, because we've made that u. Dr is just du over minus 4. What can we do with that minus 4? We can bring it out of this integral. Can we now integrate?
Yeah.
What's the integral of e to the u? We love that one because it's just e to the u. So it's going to be minus 1 to 4 e to the u. But before we can plug in our limits, you could write your limits in terms of u, but you don't need to do that on the AP exam. Before you plug in your limits, just get rid of u and put back whatever it was. So we're going to have minus 1/4 e to the minus 4r. Plug all that in. We're running out of space. Minus 1/4. I don't like this tiny board. E to the minus 4 times 1.25 minus e to the minus 4 times 0.25. Well, I guess I should have made that a bracket. And when you do all of that, you get not a lot of work was done. 0.09 joules. I basically made it up. I think I introduced the E formula with it. I don't even remember, but I just wanted an E thing in there, so I made that up. And so you got to work done of positive 0.09 joules. All right, good so far?
So basically what this means is that the acceleration is really small.
Yeah.
Or the mass is really
Yeah,
small.
we don't even know how big it is. You know, all we just know is the force. So pretty straightforward. I didn't even give you a mass or anything like that. So it could be a huge acceleration if it's a tiny, tiny thing, right? But we don't know for sure. All right, we now want to try this to energy because we know that energy is being added, energy is being removed. We said that all along, but we want to get the work energy theorem out of this. You can kind of approach it from, we're going to start with that equation for we're going to start with our equation for net work, and then we're going to get the energy, the work energy theorem. So work net, again, I can write it as F dot dr, and what force would I be putting in here?
The FA, force applied?
Well, if I'm talking about work net, it has to be the F net, right? Or we could have added up a whole bunch of forces, but we didn't do that. All right, as soon as we see the dot product, what are we going to do?
Get rid of it.
Get rid of it, so that's going to become the integral of F net cosine theta dr. We are going to assume the object moves in the direction of the net force, so we're going to say that the angle is going to be 0, and we're going to get rid of that. I think that's a decent assumption. So now we have the F net dr. What can I replace F net with? Alrighty, so we can say work net equals the integral of ma dr. Well, if F is varying, then what else is varying?
One of those. A.
A is varying, so I can't integrate A with respect to R, so now I have to work to change this. So I know A is the derivative of what?
dv over dt.
So I can put that in here, so work net, I can pull the mass out, correct?
Yeah.
We're assuming the mass of the object isn't changing. So dv dt over R. What is dr over dt? Change in position over change in time.
Velocity.
That is velocity. And we can say work net equals m, the integral of v dv. Can I do that integral?
Yeah.
Sure, and what's the object starting at? Well, I don't know, we'll call it v0. And it's ending at some later velocity. So when we do this, we get work net equals m. Well, what's the integral of v dv? V squared over 2. What just showed up? Kinetic energy from v to v0. We'll plug that in here. Work net equals mv final squared over 2 minus mv initial squared over 2. This is what we've decided to call kinetic energy, the energy due to motion, the energy due to the fact that the object has, mass and velocity. So we could say work net is k final minus k initial, or dun, dun, finally work net equals delta k. And that is, of course, our work energy theory. So if you know the net work done on an object, you can then, go and figure out velocity and so on. This is extremely helpful when you're dealing with forces that vary with position, because we can't use kinematics when we have forces that vary at all, correct? So we can't use kinematics, but if we have forces that vary with position, we can't even use that to figure out accelerations with respect to time and things like that, so we can't even get, it's a hard way to approach it that way either, to try to get a function for velocity or something. But this can help us out if they ask us, how fast is the object going after a certain, after it moves a certain position. You can go with your work net equals delta k, because you can figure out the work net by just doing a little fnet dot dr and then set it equal to delta k, and we'll see, I brought some problems where that can be, an extremely helpful approach. I don't think that is on the AP sheet, if I remember correctly. I should always bring one with me. It's not, right?
No.
Just the work energy theorem's not on there. All right, so let's try a little example with this. And we'll throw another variable force in there.
Yeah.
And again, you don't need to know how to derive any of these things for the AP exam. You just need to know how to use them all. All right, so we're going to try to move some 2-kilogram box here. It has some friction on the ground. 0.4, this thing's going to start at rest. We're going to put an applied force on here of 3x squared plus 9. I don't know what's doing that. Who knows what's giving us that applied force, but that's it. I want to find the V after the box has moved 5 meters. So I want to find the velocity. Again, I could get an expression for acceleration by just taking the force, finding the net force and dividing by m. But I have an acceleration function with respect to position. So I can't integrate that to find velocity, could I?
No.
Because I would need an acceleration function with respect to what? In order to be able to, time. And I don't have it with respect to time. I have it with respect to position. So it would be hard to try to do from some sort of kinematics, integrals, different, derivative approach. So that would be a hard way to, deal with this problem. But I do know in the back of my mind, if I have force varying with position, it's very easy to calculate the amount of work done. Because I know work is the integral of f dot dr. F varying, with position.
Is that mu for like friction?
Yeah, so I threw a little friction in here, just because I felt like it. Alright, so I want to find the velocity after this box has moved 5 meters. I know from the work energy theorem, if I can figure out the net work, then I can figure out the delta K. How much K does it start with?
0.
None, so if I find the work net, that's going to be my final kinetic energy, and then from that I can easily figure out the velocity, right?
Yeah.
So let's go in and calculate the net work. Again, my options for calculating net work: add up all the work from the individual forces, or figure out the work done by the
Net force.
net force. Which way you want to approach it?
Net force.
All right, let's go with net force. So we're going to do work net is the integral of F net dot dr. All righty. What are we doing with that dot product?
Turning it into cosine theta.
Turning it into cosine theta. All right, well, if we're going to figure out F net, we got to, if we're going to use work net from this approach, we actually have to figure out F net. So what other forces are acting on this thing?
There's Fg.
We got Fg, we've got some friction, and
Normal.
the normal force. Which ones are contributing to the net force here?
Just the friction and the apply.
The friction and the applied force. So Fa is, not Fa. F net is going to be Fa minus FFk. Well, I have an expression for Fa, 3x squared plus 9. How am I going to get an expression for friction? So we can go off to the side and say friction kinetic is mu k times the normal force. So what is my mu k?
0.4.
And what is my Fn?
2g.
What's that?
2g.
2g, because it's going to be equal to gravity y.
Because there's nothing else pulling it up.
It's not moving, it's in equilibrium in this direction, right? So it's going to be 2, again, on the AP exam, you can always use 10, right? So keep your math simple, you don't have to use 9.8. In fact, on multiple choice, you should be using 10 because you don't have a calculator, but again, we can do that. So what does our friction come out to be? 8. Well, I'm going to write joules by accident for a second. So we know that, what's our net force? 3x squared plus 1, right? I'll let you catch up. All right, now that that's our net force,
And we know that the direction for cosine is going to be 0.
well, we're going to have to assume that since friction was smaller than that alone, that it's going to be cosine 0, right, like you said. So this is going to now become a 1, and we're going to plug in 3x squared plus 1 dr. Again, do we care that the x and the r aren't matching? They're the same thing, right? So we'll just change this to a dx because they're both, again, measuring, indicating, they're just variables for position. So it's just that they give it in, maybe this new formula, the formula sheet, they'll put it as an x. Who knows? Wouldn't that be nice?
Is the formula sheet for the coming test set?
No. They usually have it published by now. I went to AP Central this past school week because I gave another test, and I always give, I give out the formula sheet.
It hasn't changed since 09, right?
No, the last one was, I think, specifically just for year 2012. I think it just says 2012 on top. Sometimes it'll say like 11 and 12 or something, but it only said 12. And when I went last week to see if there was a new one to print out, because I was giving another test, nothing's there. It says 2012. Unless I'm not looking in the right place on AP Central, but I'm going to exam information and formula sheets, and I would think they'd have the latest there. That's usually where I get it off of. So I don't know why it's taking them so long. Usually it's like, by October or something, they have it. So I don't know why. All right, what are our limits for our integral? 0 to 5. So let's do the integral and figure out how much net work was done. So what's going to be the integral of 3x squared plus 1? X cubed plus x from 0 to 5. So we're going to get 5 cubed plus 5 minus 0, right? So what is that, 120? 5 cubed is, yeah, 125 plus 5. Sorry, I subtracted instead. So 130 joules. Now we can take that net work and easily set it to what? Delta K, right? And that's going to be 130 joules, 1/2 mv final squared minus 1/2 m 0 squared, because it started at rest. Plug in everything, and what do we get for this velocity? The square root of 130, so 11 point something or other? 11.4 meters per second. So there it is. So there's a variable force using the work energy theorem to figure out how fast the object's going. Again, a nice approach for when you're dealing with forces that vary with position. Not as bad when you have a force that varies with time. If you have a force that varies with time, again, you could use impulse momentum, which you're going to learn soon. But if it's a force that varies with time, then you can get an acceleration that varies with time. Then you can use the ideas of kinematics with, v is the integral of a dt, because a is written as a function of t. So when it's position, you're really, kind of pushed into this corner of work and energy. All right, last thing we want to say about this before we do some AP problems. Just want to throw this in here because, it's not a big part of the exam, but it does show up often in multiple choice and in part 2s as well. Now, two different forces can do the same amount of work. For example, what am I looking for? A marker. So one last idea. If I had a 3 kilogram mass and I put a, what did I write down here? A 2 Newton force on here for 20 meters. Or I had the same 3 kilogram mass and I put a 10 Newton force on here for 4 meters. In both cases, if this starts at rest and there's no friction, tell me about the work being done and the final velocity in both cases. How much work would be done in this case by this 2 Newton force? It's a constant force. So the work, we could go back to just FR cosine theta because it's constant. So work is going to be, 2 times 20, that would be 1, so we'd get 40 joules. And how much does that do? Same exact thing, right? So we end up with 40 joules of work being done. If we calculated the final velocities, they would have the exact same final velocities, wouldn't they?
Yeah.
So, different forces can do the same amount of work. What would be different, though, in these two situations?
Acceleration.
Acceleration is going to be different. Which one's going to have the higher acceleration?
The one on the right.
The one on the right. Therefore, it's going to get to its final velocity faster. So it's going to get its work done in a shorter amount of time. What concept does this lead us to? The rate at which work is done. Have you done this at all yet with them?
No.
The rate at which work is done?
Oh, yeah.
What is that? Power!
It was like a whole day ago, so
So, when we're comparing works, we like to know how quickly or slowly that work's being done, and that gets us into this idea of power. The rate at which work is done. Now, if you took first year physics, you probably had an equation that just said power is you know, the change in work over the change in time. The amount of work you did divided by time. However, that's going to give us, just like if we did delta x over delta t, what kind of velocity do we get? What's that? Well, it would be, we would have a, it wouldn't be, let's see how I can hint at it without telling you. So if I just took, so I left my house this morning at whatever time, I drove up here all the way to Danbury High School, it took me like 35 minutes, and I just took that total distance divided by the total time. What kind of velocity am I going to get? Average velocity. I'm not going to get, you don't know, I mean, there was times I was stopped at lights, at stop signs, I was speeding up, I was slowing down, I got an average velocity. This really gives me what kind of power?
Average power.
The average power. So if we want to find the instantaneous power at any point in time, how big does delta t have to be? Tiny, tiny, tiny. So if we want to find instantaneous power, we basically have to take the limit of, as delta t goes to 0, of delta w over delta t. And what is that limit going to give us? The derivative of work with respect to time. So power is just the derivative of work with respect to time. Every time you can write something as a derivative, you can write it as an integral as well. What would be the integral associated with this equation for power? So work is the integral of power with respect to time. Now you got a whole nother equation for work that doesn't show up often, but it's nice to keep it in your back pocket, that you can figure out how much work is done or how much energy is being used or whatever if you just know the, you know, the function for power and so on. All right.
Isn't it confusing that DW, like, work is a W and watts are W?
Yes, but work is a variable and watts is a unit.
Still annoying.
Yes, it is. I agree. But watts don't show up. They won't show up in an equation.
Yeah.
So if you see an equation with a W in it, it has to be work. Watts will only show up next to a number in the end. So if you see W in equations, well, what's even more annoying is I'm sure you've all noticed that this is a capital P, correct?
Yes.
Because we have a lowercase p.
Yeah.
That stands for momentum. So, you know, that is very obvious that that's capital P and not a lowercase p. So capital P is power, and it's just the derivative of work with respect to time. Or I like, you know, again, this work is the integral of power with respect to time. There is another power equation. Anybody know it?
F times V.
Force times velocity, which you can derive from this whole thing. I don't know if we really need to spend the time deriving it, but an alternate, do you want me to derive it or you don't care?
Okay.
All right, do you want me to derive it or
Which one? The
force times velocity? It comes right.
oh, I derived it for you.
Yeah.
Okay, so we don't need to do
Simple.
that, so another equation we'll just put up here is power is just force times velocity. So again, good to keep in your back pocket. Power, I think, tends to show up more in multiple choice questions than in free response.
So that's a multiplication and a dot product.
Actually, I think it ends up being a dot product.
It is.
Because it is, it's taking two vectors and once again coming out and getting a scalar. So it has to be a dot product. So. All right,
Do you
so.
have any problems that use that?
What's that?
Do you have any problems that use
I
that?
have multiple choice that use FV, and then we have some problems. So we'll do a few multiple choice questions first. So that's, you know, my spiel on work power and the work energy theorem. Sorry about the line across everything. I don't know what was going on with my photocopying machine. So these, I just went back through my archives of old AP released exams, and every one of these was pulled off of an AP exam. So, well, let's try a few of them. So we'll spend a few minutes doing those. I don't know if you want to shut that off till you know, we go over them or something. So let's try a few of them, and then we'll do a few AP questions. We break